And it's time. Welcome back, folks. We're now on week 4. So the great news about week 4 is once we get through this, we're 25% done with the entire semester. So congratulations on that milestone so far. What we're working through is still chapter 13. We'll finish it off when we come back Thursday if we don't quite get through it today. But so far, the due date is sent to be a week away, February 9th. And that means it's going to be the last chapter that's going to appear on our very first exam. Exam 1 is just going to be these 4 chapters all together. It'll be a 75-minute exam, and it's kind of tricky to discuss because there's 2 sections running in one. So if you're in the online section, I sent out instructions this morning to both folks who'd rather test in the Pocatello Testing Center and those who'd rather test in the Idaho Falls Testing Center. So see your messages in the Canvas inbox system or that Google email message that it bounces to as well for the instructions on getting it scheduled. And if you're in the in-person section, a week away from today, I'll just be here right at 1 o'clock. And that's all we'll be doing today, just the 75-minute exam on that day, not today, sorry. On that day, February 9th, it means there won't be any class being held on that particular day. It's conceivable that folks want to take their exam right at 1 o'clock in the testing center. And for the in-person section, we'll be doing the exam at the class time. So this will be kind of just a exam day, and we'll be back to working on chapter 14 when we come back Thursday of this week. So that's our big announcement so far. Any questions or comments at the moment? Okay, this probably looks weird. I forgot to share the screen when I had all those comments wrote up. And if you, or excuse me, record the lecture, and if you try to unshare to get the lecture recorded, all those annotations disappear. So that's my quick fix, the screenshot. But other announcements about the exam one is the materials are going to be a basic scientific calculator. So the TI-84, that kind of stuff is not allowed on this exam, but you won't need that level of computation because like we mentioned, it's going to be a purely concept exam. So it is closed notes, but I'm attaching this formula one sheet as the very last page of the exam. Here's what it looks like. Just a quick rundown of facts, formulas, ideas, essential limit theorem makes a showing on here, for example, a rundown of parameters versus statistics, just a basic informational sheet that you can refer to on the last page while you're taking the exam. So this page is good to have at your ready in front of you as you're studying for the problem, so you know what's on it, what's included, what kind of information you have to be prepared for memorization. And for extra practice on this exam, I have 2 versions of sample problems. Version 1 looks like this. These are problems that we did ourselves, so this is the lecture notes really. I took all the examples in the lecture notes that look like they make great exam questions. I converted them over to what would they be if they were real exam questions. So this gives you a really good look at what can be on the actual exam. So scrolling through here, anything you might have noticed that requires RStudio has the outputs just produced right away. So you're just going to be analyzing what you're seeing as a conceptual exam. Even if you go down to say the normal distributions, that's a weird one because we use the calculator heavily. But again, it's going to be similar to what you are doing in assignment number 3 for chapter 11. There's a problem where we in class and you yourself will be sketching the graph of the normal distribution, shading a region that corresponds to a probability statement, and other things along the lines of making interpretations. The only downside with this kind of document is it's stuff we've done before. So if we want to refresh problems, go to version 2, and these are all brand new questions on a chapter by chapter basis for the same kind of ideas, just concept questions based off what we did in class and what you did in the homework. So that's a lot of announcements so far. Any questions at the moment, folks, about exam 1 or any of the materials? Okay, as far as the solutions goes on any of these documents, I did put solutions on the end of this one because the idea is if you want to look into the solutions, say for chapter 11, just go to chapter 11 and the lecture notes. And even though it's just the concept question here, you'll see the full solution to everything we did on that problem. Version 2 does have the solutions on the very end. And if you see anything that seems odd or just incorrect, typo or a genuine error, let me know and I'll get that investigated and fixed right away. So as far as studying for this exam, the number one thing that you should do is make sure you're caught up on the homework as much as possible all the way through chapter 13. With the grading, I'm going to start grading these pretty much the moment I have some time as they're coming in. So I'll be sending you back the feedback on every one of those chapters as soon as possible. And even if you're working, say, over the weekend, say Saturday the 7th, Sunday the 8th, if you get me your homework in, say before around 4 or 5 p.m. on Sunday, I'll make every effort to get that set graded and send you your feedback so you know how prepared you are in any one of those chapters. We do have deadlines, due dates on these chapters, but for the sake of pacing, to put something in your calculator, if you're getting, for example, assignment 3 done by the due date, you're considered fully caught up for the course. If you need to work on the weekend, maybe you're a little bit behind, that's okay. You'll still get full credit on any of these assignments. And I was going to have another thought, but I lost it. So that's my major suggestion on being prepared for this exam. Get caught up on the homework, then start looking into either version of sample problems here to get a good feel for what do these problems look like in an exam setting. I'm going for 5 questions altogether, so I can't ask everything we did in chapters 1, 2, 11, 13. I'm just going for a representative sample, an exam that you can finish well within the 75-minute time limit. I would say a well-prepared student is probably able to finish this in around 50 minutes. But any last questions whatsoever, folks, about scheduling the exam and the exam materials or otherwise? Okay, again, if you're in the in-person section, taking the exam is easy. We just come to class as normal. If you're in the online section, take a look at the message I sent you through Canvas. And if you have any questions about using the calendar for scheduling your exams, anything along those lines, don't hesitate to ask. I'll be happy to help. So let me close this out. And I had another question that was sent to me from a student in this class this morning on assignment 2. So I think that's going to be a good starting point for us. Exercise 2, assignment 2. This was a kind of interesting section because it had a lot to do with statistics and knowing when to use certain statistics versus others. And also, this is probably the first exercises where you had to give a histogram, but there was no data file to associate with this. We had to type in the data directly. So we'll start here today, just discussing this problem a little bit to give some hints on the homework itself. Very first nuisance about the homework is we're used to going to import from base, loading up the data set, but this one didn't have any such data set. We have to manually type this in. So this is part of life as a statistician working in statistics, just handling the data itself, but I'll never make you type in, say, 30, 40, 50, 100 observations. That's just becoming busy work at that point. I'll always have a file ready to go. But for something like this, where we have 1, 2, 3, 4, 5, 6, 7, 8, 11 observations, occasionally we'll have to do some hand input. So let's read what this is about. This is gave the following distances in centimeters at which a bat first detected a nearby insect. So probably to start this out, I'd write DIST, short for distance, or just the full name is fine as well. Distance gets. Now to import the data, we're just going to manually type this in, hit C to combine. And this is kind of tricky in a certain sense. We have to be extremely robotic as we put this in because any mistype is going to make the graph look kind of funny. 16, 23, 27, 56, 52. Let me know if you notice a typo, 34, 42, 40. I'll hit return just so I can have it in the same format, just to double check. 68, 45, 55. And that should be the data set. Then once we have all that, we can hit Control A, Control Enter just to make sure it actually imported correctly. And now for the histogram, the standard syntax is HIST for hist. Put in distance, hit Control A, hold Control, hit Enter. And this is what we get for the graph of this problem. It's kind of weird looking. There's no doubt about that. I'm just trying to figure out a good spot to throw it. About right here will do the job. It's a weird looking graph, It has a main peak, but it's kind of flat. So if you call these data uniform, I don't think that would be a bad description for these data. It's off from uniform on only one category where there's one extra observation here. But the thing about uniform data is that it's also symmetric. So if you call these data symmetric, I'd say that would qualify for a description. Yet at the same time, if you're thinking of this as the main peak, then there is a direction of skew, right? There's a little bit more pull to the left relative to where the main aggregation data is, these three observations. So it makes it a tricky data set. It's kind of borderline on how you describe it. I'm not going to be super picky when I go to grade these. So the only way you might lose credit if you said that this is extremely skewed to the left. Well, it's roughly symmetric. It doesn't have an extreme skew. It does have left skew. So that's an okay thing to say to these. If you call this mostly symmetric or roughly symmetric or just symmetric, that'd be okay. But you might lose some credit if you call this perfectly symmetric or highly or extremely symmetric, because it really isn't. There's a little bit of a skew to this. So great ways to describe these data could be just uniform, skew to the left, roughly symmetric would all qualify. And that makes a problem even trickier, because if you go back to the chapter 2 notes, you have to determine what are the right statistics to measure in this distribution. The chapter 2 notes gave us some guidance. It's impossible to say what the guidance should be for every single possible situation. So we wrote down 3 pretty extreme situations. This is pretty symmetric, highly skewed to the left, highly skewed to the right. Your data seems to be kind of in the middle of all those sorts of situations. So when I go to grade these, pretty much I'm going to look into what you said the data was. If you said it's roughly symmetric, well, then in that case, you probably should be using these values for roughly symmetric data, at least roughly symmetric. Measure the center with the mean, measure the standard deviation with the S, the sample standard deviation. I said that weird. Measure the spread with the sample standard deviation S. If you said it's skewed or slightly skewed to the left and you decide to go for these statistics, the median and the interquartile range, that'd be a great idea as well. I would say certainly for these data, it's skewed enough so that the sample mean X bar does actually pull away from where you'd visualize the center on this. The median probably does do a better job, and it's because of the skew. So again, I'm looking mainly for consistency, connecting the dots and the concepts. And these data were pretty borderline. This is from our textbook, almost intentionally borderline, just to see how are we going to handle this. And it gives us an idea of these tables are nice, but they're not the end all be all. If we were working harder on this kind of stuff, we would define things like skewness and kurtosis statistics to determine what is the level of skew and what are the rule of thumbs that go along with it. We measure skewness and kurtosis for our data to determine if we're going for either one of these graphs. But for introductory statistics course, we're going to mainly do this visually. And if what you said on the notes is consistent with the picture you see here and the statistics you give are consistent with what you said, symmetric versus skewed, I'm not going to be super picky when I grade this one. It was meant to be kind of intentionally borderline on purpose. But any questions whatsoever, folks, getting through this one or discussing this example 2 problem? Wherever it went. There we go. Okay, thanks for the student for suggesting that. And like I mentioned before, we pretty much start off class going over the announcements. Then at the end of the announcements, I'll always, unless I forget, and feel free to remind me, just send out a general call to the class. Any questions, comments, whether all along the lines of anything whatsoever. And this was a great question to start us out. You can always send me those questions over email as well. That'd be a great way to just have that kind of loaded up so I know exactly what to go to after the announcements. But at this point, I'll turn it over to the class. Any questions or comments so far, folks, before we get started? Okay, well, we're jumping into chapter 13. This will be the extent of the exam 1 information. And that makes the next class, when we come back on Wednesday, kind of strange because we have to push forward in our schedule so we don't get super behind and cheat ourselves on statistical methods. So we will start working in chapter 14, but if you have any questions whatsoever to start out class, When we come back Wednesday, don't hesitate to ask. I'll be happy to address all questions. But here's where we left off. We looked at a pretty busy looking graph altogether after a quick discussion on parameter versus statistic and spotting them in an example context. This graph has so much going on, but the best way to think about this graph before we delve into it is its purpose is to give us a visual for the central limit theorem. So that's truly what it's all about. And the central limit theorem is abstract enough that's good to see this in a lot of different ways. The graph, statement of the theorem, and then we'll also do a simulation to show what does this look like if we make RStudio just simulate the central limit theorem in action. So that way we get a good multi-level feel for what's going on with this abstract theorem. But let's start with the picture. I think this is a good way to begin. It ties in a brand new definition that will be mentioned a lot in the notes that'll come up on exam 1. Starts off by saying, assume we have a simple random sample of size n from some population we wish to study. So this could be a population of people, objects, something abstract. The sampling distribution of a statistic, say like X bar, for example, is a probability distribution, like the normal distribution is, that contains all possible values that the statistic can take from a simple random sample of size n coming from that population. And one remark here is I took this from a different textbook. This is a really nice one. If you just want a follow-up textbook on statistics, it's more advanced, but it's got some really nice graphics that went along with it. And in this textbook, think of Y bar being synonymous with X bar that we use in our textbook. So that's going to be the sample mean when we see Y bar. So here's the idea. We're studying a population. We require that it has an actual mean, a finite mean, an actual finite standard deviation sigma. But you know what? That's the only two requirements. Let's pause and reflect on this. That can be any population whatsoever. It's just a quantitative variable that we're studying with two parameter values that can be measured. So let's really emphasize this. This is any population. It does not matter how skewed this gets or how symmetric it is. Any population whatsoever will qualify in this graph. So once we think about this population and we want to study it, we take a simple random sample of size n, and that's the simple random sample in action following that arrow. Once we have that sample, we can now measure two statistics, the mean of the sample and the standard deviation of the sample. So there they are. But we're really focusing on what's happening to Y bar. We're thinking about the sampling distribution, which contains all possible sample means Y bar that can ever emerge in this population. And we have just one, but when you have one sample mean, that's quantitative data, you can start plugging these into a histogram. Now imagine we're doing a very important experiment, and good science says replicating this experiment in exact the way it was ran the first time is good practice to see what could happen. We keep the sample size fixed, and we take a new random sample. Here's that one down here. Now, the major thing to emphasize is because of sampling error, we probably do not have the same n individuals. Maybe someone is from the old sample just by luck, but that would probably be a low opportunity if the population is large, like say the population of all ISU students. So this is a new random sample of n different individuals, probably all completely different, which means we expect a different sample mean Y bar. And once we plot that, that's what that graph is trying to indicate. There's variation in the statistic itself, not just in grabbing the sample randomly. We get different values every time we replicate this over and over and over again. And now, if this study was extremely important, we can imagine maybe it gets repeated 10 times or 15 times, maybe 30 times. That starts to get really, really costly, especially if the sample size is large itself. But this could be done theoretically. And that's what this represents down here. Repeat this over and over and over again, as many times as you feasibly can before the money runs out, essentially. And we won't have the sampling distribution, but we'll have a pretty good idea of what it's going to look like. aggregate all the sample means into just one histogram, and the shape it becomes highly suggestive at this point. That's symmetric. It's mound-shaped, unimodal. The peak is right over here. And it looks like you could, in fact, draw a pretty good normal curve to this. It would be n, looks like it's distributed normally. And a really good guess on what n should be is, recall the sample mean, whatever we label it as, they're approximately equal to the thing you want to measure in the first place, the population's mean mu. It's a great statistic, it's unbiased. And so every time we calculate a y bar or an x bar, same value, just a synonym there, we're estimating mu over and over again. So we expect the dead-on center of this display here to be mu. It's in fact true. The central limit theorem is going to address n. It's also normally distributed, or approximately normally distributed, so we have to qualify what we mean by that. It also tells us what is the spread. We'll put a number down to that as well. So the central limit theorem is addressing these elements, normality, the center, and the spread for the sampling distribution of your statistic, y bar or call it x bar, same statistic. So all this content is the central limit theorem. But any questions at all, folks, seeing just the visual of this so far? Okay. The remark down below is just emphasizing this is an extremely big shift of perspective out of nowhere. In chapter 11, when we were first looking into the normal distributions, we were talking about not any population. We wanted populations that were already symmetric and mound-shaped so we could fit a normal curve to it. And we're modeling one member of that population, whether it's a distance, a time, or a length, based on the normal curve. But now, when we're talking about the sampling distribution, and we suspect the probability distribution is normal, we are now asking and answering these questions. What's the probability that the mean from the sample, before you even go to collect it, exceeds a certain value? That's an interesting kind of logic that we're going on, and it implies whenever there's one population you're studying, there's also a dual population of all possible values of your statistic. The sampling distribution is just the next population. And if we can connect the dots just right, chapter 14, using the central limit theorem, will tell us how inferential statistics are going to work in this class and any statistics class. That's all through this theorem right here, this big idea. Well, first thing we'll do is practice this a little bit with a population that's exactly normally distributed. So that's kind of a strange thing to do, but we're working our way through the full statement where it could be any population whatsoever. Well, any questions, folks, before we try out the next problem? Okay, we'll come back to this graph and take another look into it. And here's the next theorem. This theorem is great, but it has one side effect. It says you took a simple random sample, so that's good. We have something that represents the population. But we're also saying the population came from something distributed exactly normally with those particular two parameter values. Then, if that's the case, this theorem tells us the sampling distribution of the mean will follow exactly this normal distribution. And that's wonderful, except when you try to apply this to, say, real things in practice and statistics, real populations, be they people or objects, here's the trouble with that statement. Saying something is distributed exactly normally distributed means this curve describes your population perfectly, 100%, no error whatsoever. So if you say the heights of students at ISU follows a normal distribution, you're saying some weird mathematical function like this describes human variability in heights to the T, no percent error whatsoever. And that's not exactly true. We admitted it every time we did a problem in this section. It's just a model. There's error in this model. For some problems, it does reasonably well. For other problems, we shouldn't use it at all. And sometimes it could be highly accurate, but this is never really true in practice. Not for real world data. We don't expect exactly the normal distribution. So even though it's a nice theorem to think about, it has its side effects. And that's why we'll turn the page after finishing this example to the full statement, where we can run with any population by changing that theorem just a little bit. So this is the first big theorem that the book introduces. So if you're following along with the reading, I felt like this should be the first problem we do as well, just to get a feel for these ideas. So we're sampling from an exactly normally distributed population. This tells us the population has a mean mu. And this tells us the population has a standard deviation sigma. And now when you calculate X bar, or you could ask questions before you even calculate what's the probability that something happens with it, it came from this dual population, one where the mean is exactly the same, mu, but the standard deviation is not the same. It's going to be the old standard deviation divided by the square root of the sample size. I should have said that somewhere. Gather a simple random sample. Let me fix the wording here of size n, just to make this specific. And notice n wasn't anywhere in that statement. This makes it a little bit more better to connect the dots of where n came from. That's the size of the sample that was selected. Okay, let's run these ideas through real world context. This one's about the serum, let me know if I mispronounce this, alanine aminotransferase. I'll call this just ALT for short. And it's an important liver enzyme. We're told if you have a high ALT, it suggests there could be something going wrong, say viral hepatitis, diabetes, congestive heart failure. I think the list is pretty long, but this is just kind of like a warning light on the engine, for example, when you see an elevated enzyme here. So to address this, we're told a certain test for the presence of ALT is rather imprecise, but maybe it's fast. So there's trade-offs to things in life. This might be a fast test that you do when you visit your, say, primary care physician. They tell us the results of the repeated tests on a single specimen follow a normal distribution, which means the theorem above can be used. There's a normal curve on display here. And that normal curve has parameter values that say the mean, they're referring to mu when they say that, will be equal to the true ALT concentration, that liver enzyme, for that specimen, the particular person being measured, and the standard deviation is 4 units per liter. So they believe the variability of that test is exactly this for everybody, but the mean, well, it's going to try to measure that person's ALT, so they say it's equal to the true ALT concentration for that person, but they didn't give us a value. This is telling us that this test doesn't have any bias whatsoever, so there's possibly questions you might have about that don't know if that's fully reasonable. But let's imagine it's true for that specific test. They didn't say what the test was. We still need a value for mu, so let's keep on reading. Now suppose next that a hospital lab measures many specimens every day, and specimens with reported ALT values of 40 or more are flagged as unusually high. So these are the people who are going to get a follow-up call from the doctor's office of, hey, could you come in again? There could be an issue we need to talk about, or they might tell you, hey, stop that medication. We think it could be causing some problems. Didn't give us mu, but that looks important. So let's just try to remember that thought there. Let me highlight that. I'm running out of colors. Finally, the problem goes on to say, suppose that the patient's true ALT concentration is 35 units per liter. And that connects the dots here. We now have a parameter value. Let's highlight that. The context on this is kind of messy. There's a lot going on, but this is a pretty believable problem. So at least we have a way to see how this can go together in a real situation. So 35 units per liter on mu. Sigma is 4 units per liter. And finally, X is our variable we're going to use, is the test result for the presence of ALT. They're referring to that certain test's result. Okay, all that said and done, we're about ready to start the problem, but any questions at all, folks? Just delving through the context. Okay, it's good to take your time reading all this stuff. The context, again, sometimes gets a little bit convoluted. That's the reason I don't write exams that have tons of questions. I think 5 questions is about right for 75 minutes to give you that time to really digest this on each new problem. Now, we mentioned before in chapter 11, this is a pretty tricky question when this comes up. When you see the words probability distribution, that's a key word to tell you. You're just saying, what is the model for X? So we write X. This is a bit of a review, which is great, I would say. We put a tilde, and the tilde stands for, in words, is distributed as, or follows this distribution. The statement of the problem says it follows the normal distribution. That feels about right. I mean, the theorem above suggests we needed that to make any progress. So X follows the normal distribution, but to fully state the probability distribution, we need to pass the parameter values. So that's where these things come into play. The center is at 35, and the mean is exactly at 4. So when we say probability distribution, this is all we're writing out. And just saying it words like we mentioned before is fine. You could say X is distributed as normally with a mean of 35 units per liter and a standard deviation of 4 units per liter. But now that we have that, we can start addressing probability questions on X. Notice the central limit theorem doesn't make a show at all in this question yet. And the major purpose of example 2 is to kind of bridge the gap between what the probability computations looked like in chapter 11 versus how they'll change in this chapter. So this one's still a review problem. Find the probability that his specimen will be flagged as unusually high if the reported value is a result of a single test. And that's what X is, one test measurement. Being flagged as unusually high, we have to connect that with the context. And the context says unusually high means X, the result of the test, is 40 or higher. So when it says include the probability statement, all we really have to say for this is the probability that X is greater than 40. This is where you're in the danger zone and the nurse's station is going to call you right back to see what's going on. We just want to find that probability there. That's a fast computation. This is using the p-norm function in R. Let me move this around a little bit. Let's wipe, start over clean. First thing using RStudio is provide the values. So we'll say mu gets 35, sigma gets 4, and then I'll call this part B. Here, this will be just a p-norm function, right? P-norm 40, the value inside the probability statement, the event X is greater than 40, or if you wrote greater than or equal to 40, same value here in the syntax. Next, provide the parameter values, mu sigma that we just typed in, and be really careful with the directionality. This one's the greater than, so be sure to flip to lower dot tail is false. Doesn't hurt to write that in the context. Lower dot tail equals false. Since X greater than 40 is what we're computing. Now, let's just put in the whole statement. Probability X greater than 40 is what we're computing. If it was a less than, then we would just leave that its default value true. So here's the whole drama of the problem. We know this patient's fine. They're at 35 units per liter. I mean, they're close to a borderline. So that's the trouble with this problem. But if we calculate the probability, it's not just about the center value for the patient. The standard deviation, the variability of the test itself is part of the story here. So run this with Control A, Control Enter, and this is the probability we get, 0.1057. Or if you prefer in percentages, this is about 10.5% chance that this patient, whose levels are completely fine, is going to be flagged as having a serious liver problem, elevated ALT, and then they'll go be called back into the office. And that might not sound like a big deal, but that's potentially extremely disruptive to your life. You might have to call out for work for that. That could be lost wages, upset managers if it's one of those micromanaging corporate jobs, and so on. So, if possible, we want to minimize that. But so far, this is the story. If we take a measurement just once on this patient using a rather imprecise test, they admit, there's a 10% chance of making an error when that patient's ALT liver enzyme was completely fine. Well, close to the borderline at least. Any questions or comments at the moment? Okay, here's where the problem starts to get a little different. Suppose that the office knew that this test is imprecise and they just have the money, they're going to bill the insurance anyway. They're going to take 3 tests. They'll say, assume we have a simple random sample of 3 tests. I'm not exactly sure how they get the simple random sample part, but if they have a process, if they believe 3 measurements count as random for that day, so they qualify it as a simple random sample, that's a assessment they'll learn about in medical school maybe. But if we base this on a random sample of 3 assessments, that's not X anymore. We'll wonder what happens to the probability. Surely it should go down, right? But we can also say by how much at the same time. So the question says, first, before we get started, what is the sampling distribution of the mean for this sample? That's because we're no longer using X. We're going to average the 3 independent tests from the random sample that we got. So that's where the theorem from above makes a showing. Here it is. This is a quick screenshot, so we don't have to scroll up and down a bunch. Sorry, just trying to size this right. Now watch for the buzzword on this one. This is easy to miss. It feels like the same question that you did in part A, but it said if you had 3 tests, that implies a sample size n is 3. And we're asking, what is the sampling distribution? So same question before, but we're asking the sampling distribution for the mean of the sample. So thinking of what we did in part A, this would be X bar this time. When they said mean of the sample, it's a new value random variable we're working into, the statistic X bar on its own. X bar is going to be distributed normally like before, and that came from this statement of the almost central limit theorem we have down below. The center is exactly the way it was for X. It's just going to be 35. The concentration for ALT for this particular patient. But the variation, the population standard deviation rather, is different this time. We take the old value sigma, which was 4, coming from over here, and we divide it by the square root of the sample size, which was 3. So this is the new sampling distribution now for this statistic. Well, any questions, folks, whatsoever? Just writing down that statement there. Okay, well, with this whole statement here, the sampling distribution of the mean, we can return to part D. It says, it feels like part B, but there's that small change where we're looking into the mean. Find the probability that this specimen will be flagged as unusually high if the reported value is the mean of 3 independent assays or tests of the same specimen. We get independence if we believe the sample is really a simple random sample and anything else weird happened in the laboratory. So this word comes up again. Watch out for this. It's the difference of saying the mean versus saying a single result that makes a probability statement go like this. And it says include the probability statement. We're computing the probability that X bar is greater than 40. And it won't be the same in part B whatsoever because the probability model has shifted. Not the center, but the variation has shifted a lot. There's 3 tests coming together. And here's how our syntax would then have to shift over here in RStudio. Let me try to scroll just right. There we go. So probably next thing we should put in is the sample size n. N will be 3 in this problem. Now for part C, again, we're going to use the lower.tail idea because we're taking the probability in the same direction to the right with a cutoff at 40. So it's p norm 40 mu. Then we put in sigma, but now we divide by SQRT will be the square root. The sample size, I'll put in n, so that way we can play around if we ever wanted to see what would happen if it was 30 samples, 3,000 samples, but the question is answered at 3. Then don't forget, as I just about did, lower.tail equals false. By the way, you could just write it this way, lower.tail equals f, but putting in the full Boolean name false is sometimes the best practice for RStudios. There are small situations where the difference between f and false can't actually make a difference because there's an f distribution, I think, is the conflict that comes up. So I always write out this way just for the sake of safety. Okay, so that's the whole statement in RStudio. Hit Control A. Oh, don't hit that. Hit Control A, Control Enter, and that's our new probability. It's gone down by a lot. It's at now 0.0152 upon rounding. So if they have the time and money and they're willing to build the insurance, not the burden of the patient, to do 3 different tests using this imprecise test, the chance of being flagged as unusually high for the patient who's totally fine goes from over 10% to under 2%. That's pretty remarkable. So if that doesn't take extra time to do, maybe it just is a matter of using the blood draw already drawn 3 different times in the machine, or maybe they did something more elaborate, but if that's possible, it's well worth it. This person is not going to be bugged again. Maybe they'll be told that they're kind of close to a boundary. They're sort of close, but there's a very low chance now of getting a false positive that this person has a liver enzyme condition. Well, again, the purpose of this problem was sort of twofold: to re-practice the normal distribution, but see how these new theorems change the way our problem works for a part B problem versus a part D problem. Any questions at all, folks, running through this entire problem here? Okay, so essentially this is almost a central limit theorem. The major issue is it's not very practical in practice because we can't always assume every population is exactly normally distributed. So we weaken it by doing this. We go to the full-on statement for the central limit theorem, which says the following. Gather a simple random sample of size n. Randomization is required. We have to represent the population well in our sample, but we don't care what the population is. The thing we're implying is we're measuring one quantitative variable, and this could be the most skewed distribution you've ever seen in your life. If your sample size is large enough, then the underlying sampling distribution of this statistic, X bar, gets closer and closer, we'll say is approximately normal once again. So that's the central limit theorem, but you don't leave some certain things unsaid. We've complained before about the words approximately, and you can't just say approximately without giving some people an idea of some kind of margin of error or some notion of when the approximation is good. Here we'll attempt to say what is large enough in the sample size to overcome the skew you see. So when we say the sample mean is approximately normally distributed, we mean good approximation. And there are some really, really blunt rule of thumbs that go along with this. So the most blunt rule of thumb ever is, for most problems in practice, if your sample size is, I really should have wrote this way. greater than or equal to. Sorry for missing that inequality there. If it's at 30 or higher, most oftentimes the central limit theorem can be used. So that's a blunt rule of thumb. A lot of statistics books state sort straight out, and so did this probability book. But they also have to be honest with this rule of thumb. It's so blunt that you have to be mindful of what your population looks like. If you have a sample size of 30, we won't just automatically say, yes, this approximation is good. The central limit theorem will do the job. We have to look at that data, put it in a histogram, and assess just how bad is this skew. We'll be doing that in some of the problems later on in these very notes ourselves. And on the rule of thumb, they're honest that there are populations in existence of sample size 40, sample size 50, where the sampling distribution of the mean X bar is not normal. It's still skewed or still has other weird pathological issues. But before we delve into the next two questions of these notes, I think this is a good point in the notes to really think about what's going on here through a simulation. So let me screenshot this real quick. Any questions at the moment, folks, before we simulate this idea through RStudio? Okay, and a picture helps too. So let's jump up to this one more time. So we still have a mental picture when we're thinking central limit theorem. So here's the theorem. This is meant to be the graph, which is supposed to help us with this. It answers the question right here where we put a question mark. We have in this position sigma over the square root of n, just like in the last problem that we were working on. Really, the only thing is new is we're not going to say that populations is distributed exactly normal. We'll take any population we want to study, hope the sample size n is large enough so that the sampling distribution of the statistic looks close to this. If it does, we'll say we have a large enough sample size, and the central limit theorem will give us really excellent computational values when we do something like, say, that. We can have a really high sense of trust on that output. But there's so much going on with this picture. Here's what the simulation is going to look like next. So it's going to be this file right here. I'll never involve this in homework questions. This is more for the sake of a classroom demonstration, whenever we're looking at something so abstract that we should see it from multiple angles. I think I have it downloaded somewhere. I was in the wrong file. So here's the simulation. I'll just directly copy it in to RStudio, but let's make this a little bit bigger now. That should be about right. So here's the picture in the background that we'll kind of flip to. And now we're going to make it happen over here. After I wipe out the environment. Okay, so here's how it's going to start. I picked a distribution that I know can be symmetric, but it also can be very, very skewed as you'd like, just by moving around some numbers. So the way to work this is it first tells us we're visualizing the sampling distribution of a statistic X bar. So have this picture here in your mind, but keep in mind it could be skewed or worse when we say sampling distribution. Just depends on the underlying population and the sample size all at once. We're going to visualize the chi-squared distribution. This will come back later on in the course, so it's a good one to talk about now. This one happens to be skewed for certain values and symmetric for others. The mean of it, I'm just going to state as 50 to start. I changed it from 5 to 50. And it's always a non-negative value. The smaller you make that, the higher the level of skew. The next part here, this is a little bit of probability theory. If I state the mean is 50, the standard deviation for chi-squared is just twice that, so that's kind of interesting. And this is just a statement to collect in one variable a whole bunch of sample means. So it's doing this part. We're going to repeat sampling from chi-squared, compute a whole bunch of sample means, but just to make the memory work fast, I initialized it right here. And how many do we want? That's the replication. I want to do 1,000 random samples, 10 to the power 4. Let me think about that again. 10 to the power 4 should be 10,000 random samples, rather. That means there would be 10,000 little bubbles right here. And in this histogram, 10,000 observations. So that's what it looks like so far. But let's say the sample size was 1. We never want to do that. That's anecdotal data. All this is going to tell us, if we take the sample size and make it 1, is what just the population looks like. Let's just run it once to see how it looks. Hit Control A, Control Enter. Ignore the blue bar for the moment, but this is the population. I think run it from here to here, ignoring the last line where it says blue. Hold Control and Enter. And this is the chi-square distribution when the mean is 50. And visually, it looks like a mean of 50, right? That's where it centers. Standard deviation happens to be 2 times 50, so 100. And it still has a little bit of skew to the right, but it's not too bad. Now imagine that's the population we want to study. We want to use the central limit theorem, which means we're going to model our statistic based off a normal distribution. And we can do that for large enough values of n. Let's say initially the sample size n is 10. That's not the world's best study, but if this is a complicated sampling design, the samples are very costly to get. Sometimes if you're working for, say, a corporation or a government, dollars only stretch so far, and you have to deal with a small sample. Now we're not looking at the population any longer. We're going to be looking at the sampling distribution when we run this. When in the sample size 10, the next part of the syntax says, for every sampling we do, there'll be 10,000 of them. We're going to calculate the mean from the random sample of that normal distribution. So that's the random sample. We'll compute a mean, throw it into x bars, just our sample means. I'll repeat from 1 to replication 10,000. So we're going to get 10,000 sample means. We'll put in a histogram. And this is just going to be a normal curve drawn on top, much like we did here in the notes, to see how good it did. Okay, so let's run this once. Hit Control A, Control Enter. It got cut off a little bit here, but that's okay. And it looks like it did a great job. There was some skew in the underlying population, very, very minimal. You might have called it highly symmetric. But when we look into X bars, these are 10,000 different sample means. They fall into a histogram, which is very, very symmetric, centered at the true mean of 50 that we're expecting. That's pretty much just this picture right here that's occurring. So this is the best case. But let's emphasize it could have been any population, not a highly symmetric one like chi-squared with a mean of 50. We drop this down to, say, 1. It's skewed now, and it's skewed by a lot. This is a highly, highly skewed distribution. Our sample size is low. Recall our rule of thumb was at 30 for this. So if we hit Control A, Control Enter, I now have 10,000 different sample means. We've sampled from this population, and there's 10,000 bubbles, 10,000 different means. And the histogram doesn't look great anymore. It's skewed now, skewed to the right. Did it mean the central limit theorem broke? We're expecting that curve, and it's not what we got. But no, the central limit theorem didn't lie to us. It said for large enough values of n, and that's a pretty complicated statement altogether. If the sample size is large enough, then the picture will get cleaned up. So we'll go back here and say, do it all over again. We want 10,000 samples. They're all going to be different from the same chi-squared population, but now sample at the size 20. So keep an eye on this picture, hit Control A, Control Enter. It's still not good, but that's better. Let me go left and right like a flip book. This was at size 10 sample sizes. This is at size 20. I want that peak right here to match up with the peak right here, and it's pretty close. The skew is maybe not as bad. It was a pretty apparent skew here, trailing off. But here it cleaned up. Now let's go to sample size 30. At sample size 30, you know it's still not that great. But at this point, you would probably be okay by saying, this is a good approximation. The probabilities we're going to get, while all approximated for our sampling distribution of X bar, they're not doing a terrible, terrible job any longer. If the sample size just gets larger and larger, say we can't afford a sample size 100, that's great. We have better precision, I'm measuring the unknown mean mu, and this picture just gets better and better. Hit Control A, Control Enter, and at sample size 100, that's a great picture. Here, the sampling distribution is doing exactly what this picture was suggesting over here. At sample size 100, we have a great picture, and we can start redoing these problems. We can get an accurate value on that probability there. If there was any skew in the population whatsoever, and we had a large enough sample size, then we have some assurances that we did the probability correctly nonetheless. So that's the idea with the central limit theorem so far. Any questions or comments at the moment, folks, seeing it those three different kinds of ways? Okay, again, there's just a lot going on. It's a complicated statement. It's the most abstract thing we'll get through in this entire course. Here's the full statement of it. Visually, this is what's going on. And as a simulation, here's how we can see it change dynamically. And just for the sake of it, let's look into something that gets just really, really bad, just for the sake of fun on this one. This didn't have to be an integer for mu. We can make it say be 0.1 or 0.01. So 100 is the mean of this sample. The outputs are always positive, so everything gets squished pretty far over here, and it causes a great degree of skew. Let's say we still sample a size 100, and this is what happens. Let me try again, Control Z. See? This is not a good picture. And we have to be honest with that rule of thumb of 30. There are populations for when this happens. The skew is so bad that even a sample size of 100 doesn't suffice. But the central limit theorem is almost like magic in a certain sense because that's always a promise. This is an actual true mathematical fact. This has been proven in probability theory. It uses a lot of heavy duty real analysis from mathematics. So it's like one of the nastiest proofs ever, but you can read an entire book on it and get through it. This is a verifiable fact, and it works in the real world with real data. We just need to make this value bigger. So if we go to say 1,000 for our sample, rerun this, that's the new picture. And notice it's cleaned up a good amount. It's not perfect, but the same thing is going to happen. If we go to a sample size of 10,000, that's a sample size n, and we replicate 10,000 different times, then here's what's going to happen for a distribution which is wildly skewed. This one's pretty insanely skewed. Hit Control A, Control Enter. If you see this button here, it just means this is a heavy duty operation, it turns out, for RStudio on this computer. And there we go, we got a result. Sometimes you have to step away, come back 10 minutes later for big computations, but that looks not so bad. So somewhere between 1,000 and 10,000, we've got sample size n where the central limit theorem here works for us. So again, that's what's going on with these complicated statements on the central limit theorem. This was like a warm-up problem where we assumed the perfect situation, exactly normally distributed. But for the next problem, we're going to take off that assumption and allow for any population whatsoever. That's what we're going to get into on this last problem down here, penultimate problem down here, and a final more computational problem on example 4. Well, any questions at all, folks, with the simulation or central limit theorem at the moment? Okay, well, example 3 is more just another conceptual question because I feel like looking into the theorem, the picture, and the simulation, it's still not enough. This is one of those chapters where it's a good idea to read twice, to really get the idea in your head the first time, see what happened in lecture, and then read it again, and it's going to make way, way more sense what's really going on in chapter 13. So here's another picture to go along with all this information. This is, again, from a different textbook you could take a look into if you're interested in. It says here, a psychologist, so already you know it's going to be an interesting experiment. The psychologist measured the time required for a person to reach up from a fixed position, say sitting down on a chair, and they have to reach up to hit a push button with his or her forefinger. And maybe there's like a signal, maybe a bell, or maybe just a light that flashes. They don't necessarily specify. But imagine you volunteered for a psychology experiment here at ISU. These are some of the weird kind of things you might be asked to do. Imagine what's going to really happen. A psychology experiment always has kind of more going on than you would expect, and they'll tell you about it at the conclusion of the experiment. Ethically, they need to debrief you on what really the problem is all about. Here we're told that the distribution of time scores measured in milliseconds for a single person to once again be seated down and then on a signal, reach up and just hit a button. Simple operation. The response time in milliseconds is represented by the density curve shown below. So this density curve is just putting a curve to a sampling distribution like we did over here. So that's all that's meant by density curve. And it's an interesting density curve when you really think about it. It's got a major peak right here. Most of the people they ran an experiment, they saw the signal, they got up, they hit the button, and there's not a ton of variation between those times. But in a psychology experiment, they probably went through a lot because they may have made them do it like, say, 50 times. And maybe the first 10 times it was at a repeated interval. Every 5 seconds you hit the button. And then all the rest of them, they start messing with you, like a 30-second gap or a 2-second gap. And then they're starting to make you flustered. It said about 10% of the time, the subject fumbled or missed the button on the first thrust, and the resulting delay time appears as this second peak in the distribution. So again, this is where the psychology experiment starts to do things you don't expect. So most everyone is going to hit it around then, and if they repeat this a whole bunch of times and mess with your head a little, you might just miss because you sat down, you thought you could look at your phone, but well, the signal came up and it took you longer to hit the button now. We're told because of the two peaks, the overall distribution is violently skewed. That's always a nice description. It's very colorful language, but it fits this picture. And the population mean and standard deviation came out at 148 milliseconds. So that's the average time with the skew. So notice that parameter values move to the right. We're using parameters because we're thinking of all the outputs just as one entire population now that we're analyzing. Sigma is at 105 milliseconds. It's large due to the right skew. And now if we took all this raw data and do essentially what we did in RStudio, sample from here regarding as a population now, and plot the sample means that you'll get at various sample sizes, here's what happens. At sample size 4, the sampling distribution looks terrible. You could never use essential limit theorem. The normal distribution doesn't look right on that whatsoever. Sorry for the zoom there. But that's because we didn't have large enough values for the sample size n. So rerun the simulation. They had real data that they could work with, and they just simulated sampling from this data, taking the average of time to respond, putting all those averages, maybe calculating 100,000 averages or more, pushing the software. They'll get a histogram just like we got here, and they put a curve to it just like we did. But this curve is just as wonky, really. It has two peaks, and that's because the sample size was still short. So the magic of the central limit theorem is not what happens at small samples for very, very skewed distributions. It's what happens as you keep increasing the sample size higher and higher and higher. There's a limiting procedure here. The limit of these density curves approaches the normal distribution exactly as the sample size n gets larger and larger and larger. We can't let n go to infinity because we can't take an infinite sample size, but larger and larger the sample, the better the pictures start to clean up. At sample size 16, it's still highly skewed to the right. But at sample size 32, that's right above our really rough rule of thumb for a very pathological distribution. That's not too bad. It's approximately distributed, and now we have to make a judgment call. Is that approximation good enough? It just depends on the context. But these approximations get better and better as the sample sizes themselves get larger and larger. So again, this is just another view of what's happening with the central limit theorem. we really took this to the extreme, say a sample size 1,000, these curves are going to surely look exactly like a normal curve. Well, any questions at all, folks, thinking about this kind of strange psychology experiment? Okay, so we did some pretty heavy duty stuff looking into the central limit theorem from lots of different angles, really four different kinds of angles. And now to tie this off, we'll run through another example, much like we did on example 2, but now using the central limit theorem directly. We'll run through some computations, but then in part C, we'll admit that, hey, the values we got may or may not be accurate. What are some assumptions that we would have to make to guarantee accuracy or ensure accuracy? So here's our brand new context we'll look through. But I think that this is one of those problems where it might be a rush to get it done in about the 9 minutes of time we have so far. I don't want to split this one in the middle because this is a really important theorem. This will be our first actual computational run through with this theorem. So I think it's a good stopping point for us today. We'll end just a little bit early, just so that we can really look at this carefully and not rush through this problem or break it down in the middle. But any questions or comments at all, folks, about what we've done so far today or otherwise before we call it a day? Okay, well, thanks for your patience on getting through, again, the most abstract part of the course. Chapter 14 will be exciting because we're going to take this theorem and we're going to turn the whole thing around and say, how does this work for us to make approximations on mu itself? How does the margin of error, the thing we've been discussing, we've needed all along since the first day of the course, how does this help us determine margin of error? And all those big kind of questions. So this is the connective glue between probability, chapter 11, and finally starting inferential statistics in chapter 14. But have a great afternoon, folks. We'll be back to this on Wednesday's class.